Next one is tunnel diode, gallium arsenide device, and a laser diode and LDR. Here, we're using this tunnel diode. It is the heavily doped PN junction diode. Impurity concentration is 1 per part in 10 the power 3 as part compared to 1 part in 10 the power 8 in PN junction. And the width of the depletion layer is very small, and it is generally made up of G and GAS. And this shows the tunneling phenomenon. And this is the circuit diagram. Here, while we are going for this tunneling phenomena, here that is the carrier must have energy at least equal to potential barrier height to cross the junction, and according to the quantum mechanism, there is finitely probable that it can penetrate through the barrier for a thin width, and this phenomena is said to be the tunneling, and this hence the SK diode is known as the tunneling diode, and this is the VI characteristics of this tunneling diode. And here we are seeing the energy band diagram of a this is the energy band diagram. The energy band diagram of a PN junction. Here, it is a thermal equilibrium in which both the N and P region are degenerately dropped at zero bias. Simply, energy band diagrams and VI characteristics of the tunneling diode at zero bias and at zero current on the IV diagram. And all energy states are filled below EP on both sides of this junction. Here, this is the energy band diagram at slide forward, and here while we are seeing that the electrons in the conduction band of the N region are directly opposite to the empty states in the valence band, and so the finite probability at this that some electrons tunnel directly into the empty states, resulting in the forward bias tunneling current. And here, and also here at maximum tunneling current, this is at maximum tunneling current, VI characteristics of the tunnel diode at a forward bias produces maximum tunneling current. The maximum number of electrons in the N region are opposite to the maximum number of empty states in the P region. Next one is here the laser diode is the electrically pumped semiconductor device laser in which the active medium is formed by the PN junction of the semiconductor diode, and similar to that of the light emitting diode. And the laser diode is most commonly type of laser produced, and the laser diode had a wide range of ranges, and using that they are unlimited to fiber optic communication, barcode readers and laser printers, etc. Here, while we are considering this laser diode, it is electrically a pin diode, and the active region of the laser diode is in the intrinsic region, and the carriers, electrons and holes are pumped on into from N and P regions respectively. Where initial diode laser resources were conducted on simple PN junction diode, and here why the carriers and the photons are conformed in order to maximize the chances of recombination and light generation. And here the I region and produces the light. Hence the laser diodes are fabricated using direct band gap semiconductor, and here the laser diodes epitaxially structure is grown using one of the crystal growth technique, usually starting from the N doped substrate and the growing of I doped active layer, followed by the P doped cladding and a contact layer. And here, when the electrons and holes are present in the same region, there are recombination with the result in being spontaneous emission, and the electrons may occupy the energy state of the hole, emitting a photon with energy equal to the difference between the electron and hole state involved. And here spontaneous emission gives the laser diode below lasing threshold similar properties of the LED. In the absence of stimulated emission condition, electrons and holes may coexist in proximity to one another without recombining for a certain time, and the upper state then the nearby photon with energy equal to the recombination energy can cause recombination by stimulated emission. This generates another photon for the same frequency traveling in the same direction with the same polarization and phase at the same photon, and this means that the stimulated emission causes gain in an optical way in the injection region, and the gain increases as the number of electrons and holes injected across the junction increases. The spontaneous and stimulated emission producers are very fast, more effective in direct gap based semiconductor than in indirect gap based semiconductor. The base silicon is not a common material for laser diodes. Next one is LDR. Here, in the case of LDR, this is the photoresistor or the light dependent resistor or photocell, and it is a resistance decreases with with increasing in instant light intensity. Here, if light falls on the device is of high enough frequency, photons absorbed by the semiconductor give bond electrons enough energy to jump into the conduction band. Therefore, the resulting free electron conduct electricity, thereby lowering the resistance, and the photoelectric device can be either intrinsic or extrinsic. And also, in the case of intrinsic device, the one-day availability of electrons are in the valence band, and hence the photons must have enough energy to exit the electron across the entire band gap. And in the case of extrinsic devices, have impurities and also known as dopants, iron wire whose ground state energy is closer to the conduction band, since the electrons do not have or for to run lower electrons photons. Therefore, if a sample of silicon has some of these items replaced by phosphor, there will be extra electron available for conduction. Next one is gallium arsenide device. Here we have seen this gallium arsenide device. It is a compound of the elements gallium and arsenic, and that is it is used in the manufacturing of devices such as microwave frequency integrated circuits, monolithic microwave integrated circuits, and infrared light emitting diodes, and the laser diodes, solar cells, and optical windows. Gallium arsenide is often used as a substrate material for the epitaxy growth of other 3 to 4 semiconductors, including INGAS and GaINNAS. Some electronic properties of gallium arsenide are superior to those of silicon. It has the highest saturation electron velocity and highest electron mobility, allowing the gallium arsenide transistors to function at frequency in excess of 250 GHz. This is a result of higher carrier mobility and lower resistance device parasitic, and this property is recommended as gallium arsenide security in mobile phones, satellite communication, microwave point-to-point links, and higher frequency radar system. It is used in the manufacture of gun diodes for generation of microwave